The last section that we are going to look at for this week, and I've had to do some rearranging of your modules because I got to looking at the way that it was set up. I didn't like it. But the last section that we are going to do is something known as the mean value theorem. So we're going to go through it, and a big chunk of this video is just me kind of talking through the mean value theorem. Guys, I'm going to go ahead and tell you the mean value theorem in terms of computations in calculus is not super useful. We may or may not ever mention it again. Where the mean value theorem comes in is it's more useful when you're doing some type of analysis. So when you're doing proofs of this stuff. So if you ever have to go on in math, and I don't know what you guys are planning on doing in terms of your careers or your degrees, but if you ever have to take a class called real analysis where you're proving these aspects of calculus, that's where the mean value theorem is going to come in more frequently. Sometimes it's used in physics, but in terms of, like I said, just pure calculations of numbers, we may never talk about the mean value theorem again. So the mean value theorem is one of the most important theorems of calculus. We look at some of its implications at the end of this section. First, let's start off with a special case of the mean value theorem called Rolle's theorem. So Rolle's theorem, I believe, is where it started, and the mean value theorem just expands on this idea. So informally, Rolle's theorem states that if the outputs of a differentiable function f are equal at the endpoints of an interval, then there must be an interior point C where f prime of C equals 0. So they give some examples here. So if your endpoints are equal, at some point, this thing had to switch directions, which means that you're getting that critical point, or where the derivative is equal to 0. You're getting a max and a min of some sort. So Rolle's theorem says let f be a continuous function over the closed interval a to b and differentiable over the open interval a to b, such that f of a equals f of b, so the two endpoints line up. Then there exists at least one c as an element of the open interval a to b such that f prime of c equals 0. Now, here's a proof if you're interested in doing it. Again, Rolle's theorem is a really powerful thing in terms of analysis and doing these proofs. So that's what analysis is you're actually sitting down, figuring out why this stuff works and making or proving that it works for all the different cases, or what cases it doesn't work for. So there's a proof if you're interested in reading it. I'm going to show you just a handful of examples on how to do this stuff. So let's talk about, what else did I want to talk about? So let's talk about the mean value theorem and its meaning. So Rolle's theorem is a special case of the mean value theorem. In Rolle's theorem, we consider differentiable functions f. Differentiable, remember, just means that I can take the derivative at any spot on that interval. So defined on a closed interval a to b with f of a equals f of b, the mean value theorem generalizes Rolle's theorems by considering functions that do not necessarily have equal values at the endpoint. So consequently, we can view the mean value theorem as a slanted version of Rolle's theorem. The mean value theorem states that if f is continuous over the closed interval a to b and differentiable over the open interval a to b, then there exists a point C that's an element of a to b, such that the tangent line to the graph is parallel to the secant line. So in other words, remember, to find the secant line, you need 2 points, and you just find their slope between those 2 points. You can make your secant line using y minus y1 equals m times x minus x1. The tangent line, remember, was a lot more strict. It was the instantaneous rate of change, and therefore you have to be able to do a derivative. But that's what they're saying, is that you can find the slope of the secant line parallel to the slope of the tangent line. In a big portion of these problems, we're just going to be graphing them, kind of looking at them. Here's the mean value theorem. Let f be continuous over the closed interval a to b and differentiable over the open interval. So that's something really important. It has to be continuous and differentiable. When it asks you questions about whether the mean value theorem applies to a particular example, this is what you're looking for. You're looking to make sure it's continuous and differentiable over the course of whatever interval they give to you. So then there exists at least one point C as an element A, B, such that f prime of C is that. Guys, we have seen that formula before. That is the formula for the slope or the average rate of change, which is the slope of the secant line. And of course, f prime of c is the slope of the tangent line. Of course, in math, we have to make it sound really super complicated. Here is the proof of that if you're interested in seeing it. If you take analysis, you'll have to do it. What else do I need to do? Here are some corollaries of the mean value theorem. These results have important consequences, which we're going to use in upcoming sections. So at this point, we know that the derivative of a constant function is 0. We've talked about that for 2 chapters now. The mean value theorem allows us to conclude that the converse is true. In particular, if f prime of x equals 0 for all x in some interval I, then f of x is constant over that interval. This result may seem intuitively obvious, but it has important implications that are not as obvious, and we will discuss them at some point. So functions with a derivative of 0, let f be differentiable over the interval if f prime of x equals 0 for all x is an element of I, then f of x equals constant for all x equals element of I. We have the constant difference theorem. So f of g are differentiable over the interval I, and f prime of x equals g prime of x for all x is an element of I. Then f of x equals g of x plus c for some constant. So here's a really important statement. If 2 functions have the same derivative, they differ at most by a constant. So they're just kind of moving up or down. Guys, I can see this being more important for us when we are doing integrals. The third corollary of the mean value theorem discusses when a function is increasing and when it is decreasing. Recall that a function f is increasing if f of x1 is less than f of x2 and x1 is less than x2. It's decreasing when it's vice versa. So using the mean value theorem, we can show that the derivative of a function is positive, then the function is increasing. If the derivative is negative, then the function is decreasing. We can make use of this fact in the next section where we show how to find the derivative of a function to locate maximums and minimum values of the function. So this is talking about the first derivative test, which I'm going to talk about more in depthly. The first derivative test is not complicated, but it uses this corollary to make sense of it. And there is your corollary for that. Again, we're going to talk about that one. So we are going to look at a couple of examples here. Again, I'm not going to go really in depth with that. So for the following exercises, determine over what intervals, if any, the mean value theorem applies and justify your answer. So looking at number 153, we've got y equals 1 over x to the third. Now, one of the things that I'm looking for, remember, is I want to make sure that it's continuous and differentiable. Anytime I have an x on the denominator, I'm worried about my continuity. This thing is not continuous at x equals 3. Why is it not continuous at x equals 3? Because you've got an asymptote. Or excuse me, not 3, 0. X equals 0. Because if I was to plug 0 in for x, I'd have 1 over 0, which is undefined. So I do have an asymptote at x equals 0. Let's make a note of that. Now, that's the only spot on number 153 where I have an issue. X can't be 0. So everything else, according to the mean value theorem, because it would be continuous and differentiable, would work. So to tell what my intervals are going to be, how do we say that x can't be 0 in terms of interval notation? Well, we say it can go from negative infinity all the way up to 0, but it'll be an open interval because we can't be 0, union with 0 to infinity. So that's that particular one. Let's go on and look at number 155. So 155, we've got y equals the square root of x squared minus 4. Now, if you think about the square root of x squared minus 4, I am concerned that there is a square root. So what I know about square roots is that you can have zeros under square roots, right? You can have positive numbers under square roots. You just can't have negative numbers. So what I'm going to do is I'm actually going to pull that x squared minus 4 out. And I'm going to set it greater than or equal to 0. So if it's 0, it's fine. If it's positive or a number greater than 0, it's fine. It's when it's negative that I get concerned. So how do we solve this? Well, if I go through and actually set this up, I'm going to add my 4 to both sides. So I get x squared is greater than or equal to 4. And then to finish this out, I'm going to take the square root of both sides. But what happens is when you're using a greater than symbol actually splits up weird when you go to solve it. So it's going to split up to be x is greater than or equal to 2. Yeah, x is greater than or equal to 2, or x is less than or equal to 2. Or excuse me, negative 2. Because when you take the square root, you get plus or minus. So that's going to be my 2 intervals here. So how do I set this up? I'm going to say, okay, well, I can go from negative infinity all the way up to negative 2. And that's going to be union with 2 to infinity. All right, cool. Oh, let me clear this out. Because I think I'll stop the video there and we'll finish this out. Again, I'm not doing a ton of problems from this section because the mean value theorem is important, but in terms of like the calculations with it, not so important. All right, I'll see you in the next video.